Functional programming, remember those who took the other modules, we know Scala is all about functional programming, where functions are first-class citizens. Python mimics functional programming, so it's not what's called pure functional programming. But before we get into what's functional programming, let's get into a bit more details on different types of programming. So programming languages support decomposing the computational problems in many ways. So one is called procedural. So this is simply like C or sort of classical languages, or even a shell, bash, where you simply instruct the computer. You just tell it what to do step by step. That's classical procedural programming. Declarative programming, again, those who've taken Spark SQL. SQL is sort of declarative language, where you just write what you want it to do, and then under the hood, the engine figures out how it should actually do the steps for you, right? So Apache Spark's Catalyst, which is the optimizer underneath Spark SQL, figured out the logical plan, optimized the logical plan, and then laid out the physical plan, and optimized it, and so on. So that's declarative. Object-oriented is sort of what I do a lot of my research in. So C++ is a classic example. Java supports object-oriented. And remember, Scala was both functional and object-oriented. Python also supports objects. That's exactly what we did with ProBMap and RV when we defined our own classes and we created instances of these classes. They're essentially objects. And that's object-oriented programming. And the key thing is when in object-oriented programming, you create this object in memory, and then the object maintains its states, and then when you interact with the object, it updates the states somewhere in memory. Functional programming is quite different, right? It decomposes a problem into a set of functions, right? You know what functions are. So the classical functional programming languages, so-called ML family, is standard ML, OCaml, and other variants. I believe the functional programming course in the IT department used to use OCaml. Haskell is like a very modern functional programming. Tio, for example, is written in Haskell. Okay, so that's the main idea. And the advantage of functional programming is that we can start doing things quite mathematically now. So you can have formal provability that your program actually does what it's supposed to do. You cannot guarantee these formal provability in other styles of programming. And of course, it has modularity, where you can break the things into modules and compose the modules, and it's usually easy to debug and test. And so that's why functional programming is very useful, especially if you're into computational mathematics. So I'm not going to go through all of this. So the main thing here is iterators, right? So Python allows you to do functional style programming, and this is to be distinguished from pure functional programming, which is like what Haskell does. So it kind of mimics functional programming. Okay, so let's get into some iterators in more detail. So I'm just reading you the stuff on iterators. So what's an iterator? It's an object representing a stream of data. So that's the abstraction. So it returns the data one element at a time, and there's an infinite stream concept under the hood. So the Python iterator supports a method called next, which basically takes no arguments and returns the next element in your stream. Okay. So here is an example. So we create a list called L, 1, 2, 3, and then we say IT is iter of L. So we ask it. So if we ask to just show IT, it says it's a list iterator object. Right? And if you ask what is the type of IT, it's a list iterator type. And I can do it.next, parentheses, it'll give me the next iter. And I can do again IT of next. You see, 2 is after 1 in the list, and 3 is after 2 in the list. And the it.next, if I do again, it's run out of all the stuff because it's sort of popped everything in the stream. And it should give you this stop iteration signal. So you can take an iterator and so-called materialize it. Like that means, you know, instead of having the stream coming at you one at a time, you can basically make that available in memory. That's called materializing an iterator. So you can materialize it by just turning it into a tuple by simply sending the iterator IT into this tuple. Right? So that's the materialize iterator by turning it into a tuple. You can also turn it into a list. Okay? So it's just list materialization of the iterator. You can call functions on it. So if the iterator is just sending a stream at you, you can just apply a function that will typically act on a pair at a time. Max is such an operator, right? You can take max the stream. So your max of L will give you 3. Oh, that's a silly thing. So I should really try max of IT. Oh yeah. So this says max arg is an empty sequence because I materialized it already. So I should really say IT equals iter of L, and then it's fine, right? Because when I materialized the iterator, it just popped everything and it's empty. Okay, that's what this should have been. Now, what's a generator? Remember, we ended the previous pre-lunch lecture with naive tuple comprehension. So if I took a list comprehension and replaced the square brackets by parentheses, I said this is weird generator thing coming out, right? So that's what we're going to get into now. So a generator quickly is a function which returns an iterator. Okay. Yeah, it looks like a normal function, except it contains yield statements, and we'll see an example of a function, a generator defined with this yield statement. So the nice thing about the yield statement is it sort of mimics functional programming under the hood, and so you can think of it as you know, when the generator resumes, it picks up where it left off, in contrast to functions which start fresh on every invocation. Remember, the function, when we implemented the function as a procedure, we thought of it as a black box. It takes an input and returns an output. That's an invariant thing. But an iterator is different. It basically, you know, keeps track of where it is now, and then it can be called again. A generator, sorry. Now, what are gen X's or generator expressions? So this is an expression that returns an iterator. It, again, looks like a normal expression followed by a for expression defining a loop. Yeah. So let's look at some examples. So these are called list comps and gen X's, like list comprehensions and generator expressions. This sort of functional lingo plan. So here is the basic syntax for a generator expression. There'll be some expression, say some arithmetic operations, whatever you're doing. And then you have for expr in sequence 1 if a condition is satisfied. So it's already a conditional gen X, right? Just like conditional list comprehension, we have a nested conditional generator expression. Yeah. That's the general syntax for it, and that's what we were doing earlier when we just put parentheses in the list comprehension. So this is just from the programming guide, a nice example. So let's say we have a line list, which is a bunch of strings with end of line. And here's my list comprehension, where I'm simply stripping the end of line for each line in the line list. So this is my classical list comprehension. And this is the equivalent generator expression, right? So this, remember, we just put parentheses, and exactly the same as list comprehension. So this is the stripped iter, and the other one is a stripped list. So stripped list just removes the end of line. character. And then if you do the type of the stripped iter, it will now give me that is a type generator. Right? So this is different from my stripped list, which materializes the list directly. So if I ask what is stripped iter, it says it's a generator object. And I can materialize it by calling list on the stripped iter. So it just now will materialize that generator expression and give me a list back. So this can be powerful down the road. So if you want to, implement some even realization of some infinite stream, it could be. So actually, Tilo is writing some code on scalable density estimation. So there he's using Scala's functional programming primitives to define infinite trees. So although you cannot represent the infinite tree in memory, you can use these functional programming primitives to at least implement these structures in this sort of generator specific way. So of course, because I materialized it, when I turn that into a tuple now, I get an empty tuple. So again, we're just doing this anew. So I'm materializing it as a tuple directly before I exhaust it. Once again, list of stripped iter will give me an empty list now because I have already consumed it when I materialized this tuple. Okay. Yeah, so this is a bit more. This is exactly what I copy pasted, and I learned about generator expression only like it's not here, just a couple days ago. So, I mean, the other thing is like you guys should now be bold enough to go and figure out all the stuff here on your own, right? It's not rocket science, right? So here is my generator. Now I have a actual generator that's doing an interesting arithmetic operation where I take x squared for x in 1, 2, 3, and of course I have a generator, and I can do the same thing now, right? Next, 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 and then of course I'm going to hit my stop iteration thing when everything is exhausted. So then we can pass a generator to a function like a sum, right? So we did the same before with max, but we can just do this in sum. So anything that operates on 2 things at a time, you can pass it. You can pass a stream from a generator into it. Okay, so this may or may not come in handy. I don't know, time is flying by, but I thought let's put it here. Maybe we'll do something. So, so if you just go a little deeper into the same docs, you will start figuring out how to actually implement a generator as a function, right? So here's the simplest example of a generator function. It has this keyword called yield, right? So it's not returning something, it's yield. So this function, or any function that contains the yield keyword, is immediately turned into a generator function, right? This is some Python bytecode magic in the compiler under the hood. But so for us, let's just look at an example. So gen equals generate underscore ints is this function upstairs of 3. So it's going to basically create me an integer starting from 1 to 3. And then I can do the same. So now I've created, 3 integers. And I'm going to hit the stop iteration. So now, what is this? Just to get you going. So if you look at all the methods that is available, you can close the generator, and I actually don't know what gi underscore code is. Look it up. And you can throw and send, and so I don't know. I'll just but we may do some simulations using generators later. So this is Pascal. This is this advanced purely functional programming language. So if you want to do proper functional programming, you should really do Pascal and not Python. Python just mimics it. And you can't do any proofs in maths with Python's style of functional programming anyway. Okay, so yeah. So this is where I learned a lot of the stuff I was showing you guys, data structures tutorial. So that's where probably want to go to for more information. Okay, so are there any questions up to now? So I kind of started this. We may come back to this later to take a break. So this is again a bit more on list comprehensions and New Zealand earthquakes statistics. So I thought we can try and do a live data fetch of earthquakes from New Zealand and try to handle this this file, like kind of tutorial. You guys can try to battle with it because you pretty much know about try catches from the previous example with the New York Powerball. So it's maybe a good idea for you to try and do something. I'll just sort of walk around. But we'll probably come back to this later. But this is what I did. So I basically went to this website, quakesearch.geonet.org. So this is how this looks. Okay, so you can specify the zoom level. So that New Zealand has sort of 2 main islands. This is where I used to live for the last decade, Christchurch. It's very beautiful. So you can zoom into a part of New Zealand, or I just took the whole country, which will be a lot of data depending on what you want to do. And then you can choose, I know, last month or last week or last year. Maybe just choose last week, just so the file is small. So the data file we have already in the directory for you is 1 year of data. So, and then you can basically, yeah, depth and magnitude. Yeah, so I'm going to take all the different depths and all the different magnitudes. So depth is the epicenter of the earthquake, how far below sea level. Magnitude is how heavy it is. So then, let's see, build query, I think. I don't remember what. And then choose the output format to be CSV. So, you know, we know about GeoJSON from Marina stuff. KML is Google's Earth visualizing thing, right? It's Google's XML thing. So you can overlay that on the Google Earth thing. But we'll just do CSV. So we're just learning string processing. I think you just hit search. And then it tells you this little URL that you need. If you put a year, it'll give you multiple URLs because there's rate limits on how much you can get per call. But I suggest you just do this because I tried to directly curl on wget. It's more messy. So then you get this file. Now, name this file my_earthquakes.csv because there is a file called earthquakes.csv already. And then put it inside this data folder. Did I do it fast? Okay, so basically you see wherever you're running this from, if you are running it in the directory where we unzipped this morning, you will have these folders, right? So I'm basically saying name this file my_earthquakes.csv. You know, it'll come as earthquakes.csv, so I just added my_ or whatever, some other name, and then put it inside the data folder in your current directory.
And did you just say download, or did you?
Oh no, you hit the download button. Yeah. Yeah. So yeah, good. So now hit download.
Did you do that?
Oh no, I didn't. I left everything alone.
Oh,
because I just wanted everything for the last week. Don't need too much.
last week.
Yeah, so just take last week, so it's not too big.
And then
No,
you said open the file.
no, just save file. Because then it'll open in the other. Yeah, put it in the Oh, no.
I think we should.
You already went on. It's here as well.
Oh.
Yeah, because there's already earthquakes on CSV in the data folder, right? So don't override it. Okay. So that's that 4.1 MB file is the one I downloaded for everyone. It came with the zip because because then when we analyze stuff, we will all get the same results. Otherwise, okay. All right. So that's sort of your maybe or at least those who are here, we can turn that into an assignment tutorial session later, so then you don't have to do homework. But for now, I want to continue with the content first. Okay, what's the plan here? Yeah, so I'm just checking. So you should be able to see all these HTML or I don't know. You only have .ipython notebooks in your if you list right, because I can put the HTMLs there. And then if you now do %ls data, you'll have earthquakes.csv and my_earthquakes.csv. It's too small. Okay. And I will sort of let you play with my earthquakes later on your own. But let's look at the first 3 lines of the file I downloaded for you. This is for a whole year, right? So I'm just doing head -3, and so I see that my first header line has all this column of headers. So it's public ID for the earthquake. The event type field is empty. Origin time, modification time, longitude, latitude, magnitude, depth, magnitude type, depth type, and so on and so forth. Like minimum distance, yeah, this is all like the earthquake engineers know what they're talking about here, geologists. So we will just later on. I just want you to grab, the origin time and longitude, latitude, magnitude, and depth. So 1, 2, 3, 4, 5. Okay. Yeah.
The data.
Yeah. So did you download the zip file this morning?
I looked at the Git now also, and I didn't.
So you did download the zip file from the Git.
I guess
it's still right. It's in the archive. So there's a link directly from the web page. That's the zip you need to be. So you need to download that zip in the morning and then unzip it and then run the stage. What is it? Stage-n Jupyter something. So yeah, then all of this will make sense. Okay, and then this is just the last 3 lines, so it's quite a lot. And this is a nice command, WC. WC, I think, stands for word count, if I recall correctly. So that's man WC. Print new line, word, and byte counts for each file. Yeah, so it's a very useful command on shell. It just lets you, so if you do WC-L, it counts the number of lines in a file. So that's all I did here. So it says there's 21,017 lines in that file, right? So this is what we will, I want you to, so I guess let's make this assignment or whatever we want to call it. So let's see, grab, I can't remember the exact field names, but origin time, lat, long, magnitude, depth. Yeah, these are the fields, 1, 2, 3, 4, 5. So this will be our sort of little exercise later because okay, so we'll come to that later. Yeah, and I guess what I want you to do is once you process this file, I want you to start doing various statistics, right? Whatever, empirical distribution function, mass function, you know how to plot any point in 2D, same in 3D. So I want you to sort of play around with the data with graphic primitives and list comprehensions. But for now, let's jump to '07. Do you guys also have '08 in your zip? Yeah. Okay. Okay, so this is a kind of a topic slightly trying to demystify what's happening with the pseudo-random numbers under the hood, like random and things like this. So we're going to take a detour into modular arithmetic and a specific kind of pseudo-random number generator called a linear congruential generator. This is not the generator in functional programming we saw, it's just the name of this. Okay. So these are the topics. And then there's another little assignment on extending the simulation of a drunkard's walk. So only make the drunkard go left and right, and your exercise is to make the drunkard go left, right, up, and down. And then the more fun, challenging exercise is to make the drunkard go left, right, up, down, and below, above. But you'll see it. That's the assignment in the bottom. So what is all this about? So the question is, I told you, how can we, that we can produce realizations from the uniform 0-1 random variable, and if we can, then we can transform them to other ones, right? So this is the so-called fundamental random variable. But how do you produce samples from it? N samples, little x1 through little xn, from this capital X1 through xn, that's IID uniform 0-1. So, and we've been doing this already with the black box, right? We set random, and then it gives me some number, and then I hit again Control Enter, gives me another number, and so on. So it's what's really going on. So the answer is modular arithmetic, right? And number theory, and that's what gives us pseudo-random number generators and some kind of guarantees in some sense that their performance. And of course, the million-dollar question is, why do this? Why do we simulate from uniform 0-1 random variables? Why bother at all? Well, that's because we can simulate from uniform 0-1, then we can simulate from anything else. Okay, and what is anything else? Like modeling traffic queues on land, air, and sea for supply chain management, like making sure your potatoes come to your grocery stores from wherever it's grown in the most optimal pathway, right? That's a lot of simulation under the hood, and those simulation algorithms have to have certain guarantees. Otherwise, the insights will be, not good for this kind of apply to OR problems, operations research problems. Statistical surveys, official statistics, all sorts of things where you're trying to, fill missing data in a systematic way. Again, you need pseudo-random number generators, and without accounting for missing data, you really can't make sense of a lot of official surveys. Helping a hospital manage critical care for preterm babies. This sounds pretty crazy, but it's actually heavily driven by pseudo-random numbers. right? Because you have all these measurements of like the lung capacity of the baby and all sorts of measurements coming out of the incubator. And then you need to understand some kind of behavior, expected behavior, how the system will react. And these things are very difficult to do analytically using just maths, right? And in general, that's what happens with Monte Carlo methods. And in fact, if you look at it, the history starts for the same reason. The modern history of Monte Carlo it starts in Los Alamos when Ulam and von Neumann and all these guys were trying to build a bomb. So, and so here's the Wikipedia page on it. Yeah, statistical physicists really took it hard. 50s and 60s really pushed it hard. Okay, so let's see. Just want to get to the history. Yeah, you can estimate various quantities with it and so on. So, Buffin's needle is this old experiment done to estimate pi, right? This is Buffin lived a long time ago. Yeah, so here is Enrico Fermi doing some experiments with diffusion. And then the modern version of Monte Carlo methods was invented in the late 1940s by Stanislaw Ulam. By the way, he's one of the main fathers of what's called numerical scientific computing today, right? So while he was working on nuclear weapons project at Los Alamos, immediately after Ulam's breakthrough, John von Neumann understood its importance and programmed the electronic numerical integrator and calculator, right? ENIAC. Oh, wow, that's cool. Displays images now. Cool. So yeah, that's basically the birth of Monte Carlo. And then I think, it had to do with figuring out, radiation cascades, how to have enough critical material to start off a reaction, basically. Some of this history is actually, I don't know if it's here. So I had this professor, Steve Strogatz at Cornell, who's a really interesting guy. So he wrote a book called Think. Let's see, this is really fun. History. Oh gosh. Think. It's like a popular maths book. Yeah, so talking about it. Yeah, the emerging science of spontaneous order. It's quite a cool book because it goes into a lot of the history, but like personal conversational history that's not in Wikipedia, I'm sure. If I recall correctly, it was Ulam's uncle. Yeah, I think it was somebody's uncle, not von Neumann's uncle, but he had a gambling problem, so he would randomly actually pop up to Los Alamos for money, and the story is that pretty much every time these guys would get stuck on the maths, like they cannot solve it just using pure maths or analysis or whatever, blackboard maths. They would this guy will pop up, and then von Neumann had this primitive thing called the middle square method, which is one of the older random number generators. So they used that all the time when they got stuck to get out of the problem, but then he would come up. So this became the code word is Monte Carlo Casino. Anyway, it's somewhere in this book if you want to get into it. Okay. So yeah, later on when we do hopefully Markov chain Monte Carlo, this whole method carries over further to simulate dependent random variables, not just independent identically distributive stuff, but more interesting things. So this, I said earlier that perhaps the most used algorithm is the Metropolis-Hastings algorithm, and that essentially is a further extension of this work. By the way, Neumann, Ulam, these guys are actually pure mathematicians, physicists, electrical engineers. They were kind of everything, right? I mean, this von Neumann algebras, and so, I mean, yeah. So now humans have specialized a lot, but they established entire fields. Okay, let's get into what is the starting point for Monte Carlo methods. It's actually modular arithmetic. This is just arithmetic modulo M. And that's what essentially will allow us to have machine implementations of probabilistic objects. Right? So, so this is basically modular arithmetic, right? It's clock arithmetic. So you go from 0 up to some m minus 1 entries, and then you just you add, you go forward by 1 tick, and you subtract, you wind the clock backwards, and the multiplication works the same way. Okay, so let's look at it a bit slowly here. So we already saw the percent sign is the modulus operator. So 14 mod 12 is just 2, right? So what is the remainder after 12 goes through 14? So if you have a list called 0 to 23 hours, then we can use this range to get it. Now let's just print that. That's our 24-hour clock. And then I'm just doing a list comprehension where I take x mod 12. So now I just get my AM and PM. Okay, clock. And if I convert to a unique set of elements, then I see that, yeah, these are the usual numbers. For x mod 12, 0 to 24. So if m is 12, m is basically our, what are we working with? Modulo. So when we add 8 plus 6, we get 14, but if we do the addition in modulo 12 arithmetic, then it's just the remainder that matters, which is 2. So if it's 8 p.m. now, then what time will it be after I've spent the 6 hours that I'm supposed to dedicate this week toward this course? $2 a.m., right? I don't know if I put the answer here. Yeah, 2 a.m. Okay, that's what you're supposed to do, get HB in Uppsala. So modular addition and multiplication with numbers modulo M is well defined, and it has these following properties. So A plus B is B plus A. So addition modulo M is commutative. Multiplication modulo M is also commutative. So the order in which you do the operations don't matter. It's just like real arithmetic. And A times B plus C is A times B plus A times C. So multiplication is distributive over addition. So these are familiar properties, right? That looks like what happens on rings. So if A is co-prime to M, what is co-prime? That means it's not divisible by any of the same prime numbers. Okay. Then there is a unique B mod M such that A times B is 1. Okay, so these are the basic properties of addition and multiplication modulo M. So now let's get a visual understanding of modular arithmetic just to get going. So let's say we make a matrix of results from addition and multiplication modulo M. So the way we're going to think about an arithmetic operation over a set M is merely as a function from the Cartesian product M cross M. So now this blackboard form M is simply your modular your numbers 0 through M minus 1, lowercase m minus 1. So now what is this? So star could be addition or multiplication, right? So I'm just using star as a generic arithmetic operation. So this arithmetic operation is a function that has as its domain 2 numbers, right? That's the input to the arithmetic. and the output is just another number. So this is a way of thinking about arithmetic operations, as functions. So we can also think of this as a tuple, right? As a 3 tuple. So x1, x2, and x3 is an element of m cross m cross m, where x3 is simply the output of the operation. So it's all the same thing, right? It's just how you can think of arithmetic. So now let's create a matrix. So this is a Sage matrix. So in Sage, you say 2, 3 to specify a 2 by 3 matrix made of these elements. So it'll do this way. Take first 3, call it row 1, the second 3, call it row 2. And then you can ask what's the type. Well, so this is Sage matrix, right? It's not NumPy matrix. So you can do hardcore maths on this, right? I mean, do series algebra and everything else on this. It's a Sage integer dense matrix. Okay, that's because I type inferred these things to be Sage integers, and it has this, and you can, there's a lot of properties here. For example, so if I do my Sage dense matrix dot, so look at this, you can say. There's quite a lot of anti-transpose, anti-commutative error automorphisms. So this is hardcore algebra. So let us list all the 3 tuples for addition modulo 4 next. So what I'm going to do is, I want to know if I take I to be an element from 0 to m minus 1 and j to be one of the elements in 0 to m minus 1, I'm going to create my 3 tuple. Remember I said this is just a way of looking at arithmetic. So that's what it is. So 0 plus 0 mod 4 is 0. 0 plus 1 mod 4 is 1, and so on. 1 plus 3 mod 4 is 0. So now I'm simply just third element of the 3 tuple. I'm going to fix the first 2 elements on a nice matrix, right? And I'm going to only look at what the output of the arithmetic operation is. So for that, I just grab the third element like that. Yeah, so we are just going to make this matrix. Right, because now I say it's an m by m matrix, and this is the values of the addition modulo m for I and j going from 0, 1, 2, 3, 0, 1, 2, 3. So I'm thinking of it as the output of the operation. That fixed grid of inputs. Okay, it's the same for multiplication. So let's visualize modular arithmetic a little bit. Okay. So what these colors are telling you is just the numbers between 0 to m minus 1 in gray level. So I'm just sort of showing you exactly this thing in a picture, these colors in a picture, right? So 0, 0, 0, 0, 0, so this will all be black in this picture. This is all 0, 0, 0. So this is for multiplication, this is for addition. I'm going to make this a bit smaller. So I can change this, for example, to 21 modulo arithmetic, and I look at the output of multiplication and addition as numbers between 0 and 20. And as you notice, 0 times anything is 0 modulo whatever, so this top things are like that. And yeah, and then this diagonal is 0 again, because if you take 2 things that are close to m and they'll be arranged in a diagonal, you get 0 back. So this is the way to appreciate that arithmetic modulo m gets quite interesting quite fast. So let's just go all the way to 200. So this is for Dan and the other dynamical systems people. So but I mean, just multiplication and addition you can have a whole career on. Just looking at expressions and what happens to a map by doing the same thing. You get into really interesting pure math problems very quickly. Okay, so, and this will be our main ingredient in our linear congruential generator, so they can become very complex.
Using modular arithmetic and you're going to see pseudo-random number. So you use chaos for constructing?
No. I only use the word chaos now. Just addition and multiplication. I'm just saying how complex multiplication is depending on how large m is. So we're going to look at m's that are so large, and there's properties that they have to satisfy. They'll be prime numbers. Just to show that, you know, the pseudo-random number generators, good ones are quite good because they are building on, nice properties of arithmetic. So what I wanted to show you quickly is so here. Let's answer these questions quickly. So if you take m close to 200 slowly and see how these outputs of the arithmetic operations change, you see this almost looks like a nice, smoothly behaved thing because m is so large, but then when it was coarse, you saw different things, right? So you can ask, why is the top row on the leftmost column of the multiplication table always black? It's already told you, right? That's the 0 times thing. Why is there an anti-diagonal block in the addition table? The leftmost table. So this is the anti-diagonal, right? Okay, you should understand this. I'm not going to just turn everything into words. But so this is basically properties of arithmetic, right? Why are there two halves of each table? The two pictures are symmetric about the diagonal. So if I put a diagonal this way, you see that they're symmetric. Why is that? Because yeah. Oh, good. You said commutativity. Yeah, exactly. So, and these things are built into this. So now, let me just make this slightly bigger. So let's do a U-try. Okay, so here we're just taking this apart, right? So m is 4. I want to make a list form add, or I'm just adding it. It's just the pieces of the puzzle, basically. So then, we saw before, this is basically the list comprehension that's doing a double duty, which is just a recall of list comprehension, for loop inside another for loop. And so this is basically how those interacts above are created, right? And, so main reason we're using Sage Math is because it's built by a lot of very, very clever people and all over the world doing maths. And unlike Mathematica, Maple, and all these proprietary softwares, MATLAB, everything is open all the way, right? So what I mean by everything is open all the way, so it says this is a type matrix, it's a constructor for matrix factory, and here it says the file, right? It's a PYX file, which is, Pyrex. So I can do %% and I can cat, which is concatenate the whole file. There's nothing secret here. I mean, I can do this in Mathematica. It'll stop at a certain level because it's proprietary code. And there's a whole movement of computational mathematics where it started a couple decades ago. But if you are implementing something in computational mathematics and you say you've proven it, but then you're not able to show me the code all the way down to the bits, then I don't believe you. So that's one thing. And also, for every specific operation, it's using the best provable, publicly available algorithm under the hood. So that's maybe that answers your question over the smoke break, right? So this is why, like, I'm trying to, get into or show you guys Sage. Okay, so let's try creating a matrix for multiplication, just as we did before. So what will you do here? Yeah. What is the non-empty expression in the list? I mean, this is
We can just grab it from.
Yeah, I know. That's what I'm doing, but yeah.
Switch
I mean,
design.
yeah. Or let's do this, right? So let's do this from memory. What are we doing? So I times. What do you? Yeah, tell me the expression.
Times J.
I times J.
Yeah. Modulus or percent n.
Yeah.
For I in range n. For J.
Yeah.
In range. Yeah.
I mean, just so that it looks like we're doing something. So much there. Okay. Yeah. So that looks good. Okay, so now we're going to move into modular arithmetic in Sage Math. So what we were doing is modular arithmetic, sort of using it. So now if you say mod, capital Mod 812, it gives me the number 8, right? So this is the mod command in Sage Math, not Python. Now I can say my mod int is mod 812, and my mod int is of type. Look at this type. It's stage rings, finite rings, integer mod int. Now it's doing some beautiful maths, right? It's not just an int. So now you are in a ring, as I said. It's commutative and distributive and associative, right? All those properties are satisfied. And so now we're it's just a finite ring. It's finite because there are only finitely many elements. And the whole magic of pseudo-random numbers is to make M very, very large, that this finiteness kind of doesn't matter in simulations. And that's what we would like to prove for a good pseudo-random number generator. And we cannot do this otherwise because, yeah, I mean, you have to work with finite objects in the machine. I don't know if quantum computing will ever become reality in my lifetime. So this is so you can ask what's the parent of my mod int, because my mod int is just an int, right, of that type. If I ask what's the parent, it's the ring of integers modulo 12, right? It's very clear what it is. So it belongs to that parent type, parent class. Okay, so we'll compare this with our usual int for just checking stuff. So this is just our usual Sage rings integer, right? And if I ask what's the parent of my int, it's an integer ring, right? ZZ. Okay, so now I can do addition directly to my mod int. I don't have to worry about the percent sign or anything because it's already well defined. Okay? So I can just do my mod int plus 6, and my int plus 6 is 14, of course. Multiplication, right? So if I take my mod int and multiply it by 6, what happens? 6 8s are 48, 12 4s are 48. So I have remainder 0. My int times 6 is of course 48. So yeah, so basically we're just doing modular arithmetic. So you can do more interesting things like this. You can ask what is mod minus 45 of 22. Yeah.
So now when my mod int is of type, whatever type you have, it will always behave like according to
Yeah.
previous.
Yeah, right, because its parent class is just whatever rings modulo or something, right? What was it? Ring of integer modulo 12. So it will belong to that class, right? So I don't want to use like the class and object and all this because I'm such a bad person to learn programming from. Because I think in C++ and then all these words I'm using are very abusive, like proper Python people will punch me. There's the right way to say these things. I'm glad I'm not in IT, but you should really take a computer science course to learn these things properly. But you know, it's it's an abstraction that there is a parent and then this is a child and there is some hierarchy of types. Okay, so yeah, so this is the year I was born. Sorry, yeah, so I'm 45. Actually, I'm 44, but it's a plus or minus 1 problem here. So I can do mod minus 45, 2018, and I'll get my birth year. Right? And this is just same thing. What's an hour before midnight, right? I find the Swedish really interesting. Talk about what is the minute after the 15 minute before midnight, like the way you break time. It's interesting. Must be the climate or something. I don't know, man. You don't do that in South India. It's like, whoa. I guess things can change quickly. Okay, so let's do a little U-try here. So can you create the number giving you the year of birth plus or minus 1 year? Yeah, so oh. Yeah, so that's plus or minus 1 year of my older daughter's birth year, right? So, almost 15. And my younger daughter's birth year, yeah, born in 2005. Okay, so yeah, so this is maybe too rudimentary, you know. So I can define now to be mod 1012. So let's say it's 10 a.m. That's what this image is showing. It's a clock, and you can add minus 1 to now. So now minus 1 is 9, right? So that's what's happened. Just move backwards and subtract 13 from the previous expression, and you know, you keep going like this, right? So now minus 1 minus 13 is 8, right? So I just went all the way back further 1. So this is just yeah, maybe this is too boring. Okay, so and multiplication is, yeah, just the same, right? You just jump by multiplications. Yeah, these are things I want you to try later to kind of get into this a bit more. what happens if you try arithmetic with two modular integers? Does it matter if the moduli of both operands are the same and things like this? Just to kind of crazy way to learn math, right? Code it, see what happens. It's not a good idea, but it's not bad. But you know, this is something you should take a algebra course, a usual abstract algebra course. This will be your most basic objects you play with, finite rings. Okay, so this is just warm up for our main topic, right? It's called linear congruential generators. So an LCG is a simple pseudo-random number generator. So it's called PRNG. So this is the formal way to refer to all the random numbers we're using in the computer. Because they're also real random numbers, right? This is a whole branch that studies this, and you can get random numbers from machines, and it's a whole different world. So pseudo-random just means, you know, false, right? Greek etymology. So we look at what we mean exactly. So what is a linear congruential generator? It's basically has these ingredients. So it has the modulus m for the arithmetic. It has an integer multiplier called a, and a has to be somewhere between 0 and less than m. And it has an integer increment called c. So c is again between 0 and m. And it has an integer seed x0, again just some number, m. And then we have an integer sequence length n. Right? So how many samples do you want from your linear congruential generator? That's the n. So once we have all this, this is exactly the algorithm, right? So the next element, xi plus 1, is obtained from mod axi, you know, mod of a times xi plus c, mod m. Right? So it just has a multiplication and addition, that's it. As simple as it gets. And this left arrow is called gets in pseudocode lingo. It's just a pseudocode for assignment operation. Okay, so let's define this function next. So we're going to have parameters m, a, c, and x0. And, and we're going to return a list of length n, how many ever samples you wanted. Okay, so the function is literally doing exactly what we want. It takes these parameters, and then it sets x to be the initial seed where you want to start it from. And then the return value is going to just be mod x comma m, right? Because that's the first value. So you start the list with x equals x0. And then here is the, so then you go from 2 to n plus 1 in increments of 1. And then you do the following. You update x to be mod a times x. So now this x is the one from outside, right? This seed is going to be the first x when I is 2. And then you just keep updating x like this. This is how you're implementing this pseudocode, right? This gets, that's all there is. And then you append it, so you keep adding to this return value, and you return the return value, which is your list.
Quick question.
Yeah.
How come you have a small mod in your folder and not the Sage mod? Is there a reason for that?
So
Is it too heavy if you scale it up?
I don't know. I think I might be doing it because of speed. I'm not sure. Probably. We can change it and see, but yeah. No, this is just mimicking what will be usually done in a linear congruential generator. We don't need, here I'm starting the list with x0 like this. So yeah, Okay, let's look at. Let me just look at what this is actually. Oh, sorry. Yeah, this is just Sage mod. You can do mod in Python, I think. Mod is only Sage thing. So yeah. So the lowercase mod also gave me mod.
Okay, fine.
You can use the lowercase version. Yeah. Okay. So I was doing what I. Okay, so let's play with this first. So the linear congruential generators can be good, bad, or ugly, right? So all linear congruential generators are not equally good. So some are really bad for generating pseudo-random numbers. So maybe one of the most desirable properties of a linear congruential generator is to have the longest possible period, right? So you're giving some m. So ideally, you want your orbit, where you start somewhere and hop around, right? You want it to have the longest possible period. That means you don't want it to revisit the same number again. You want it to hop around so that it visits all the m distinct numbers. That's what it means to have the period, longest period. So let's first assign some values to some of the variables to pass as arguments to the function. So I'm making up one. M is 17, A, the multiplier is 2, the increment is 7, and my seed is 1, and I want 18 samples from it. And I chose 18 because I just want to see, how I want it to be of length 18. That's the longest the period can be, so I want to see how what happens for the longest possible period here. So when I run this and create this in this list L1, I start seeing 1, 9, 8, 6, 2, 11, and then again 1, 9, 8, 6, 2, 11. So I start seeing repeating patterns, right? So it just hops in the same way. So if you just convert it to a set and order it, so you see that it doesn't have all the elements between 0 and 16. So it doesn't have the longest possible period. Now let's leave M, A, and C as it is, but just change the seed from 1 to 3. Now let's see what happens. So now it goes from 3, 13, 16, 5, 0, 7, 4, 15, again 3, 13, 16. So it's again giving me another pattern that is of period 8, not of the maximum period 16. So yeah, this is our distinct elements there. So in the worst case, you can have a seed that's stuck at 10, right? I just changed the initial condition to 10. So if you land in 10 on this LCG, I'm at 10 forever. Not a great random number generator. So yeah. So a linear congruential generator is just a discrete deterministic dynamical system. That's the branch of maths that studies things like this, but much more complicated than just the multiplication and addition. So it's a discrete system because there are finitely many elements. Okay, it's discrete. It's dynamic because it's the same operation you do again and again, right? You start with the seed, you do some operation, it jumps back to some other point in the space, and then you do the same operation, it jumps to some other point. So it's called a dynamical system because it's studying how things are moving around in the same space. It's the dynamics on the space. So yeah, this is, so the way these guys talk about it, the dynamics systems people, is they will say that there's a fixed point at 10, because if you stop there, you stay there for good, right? And these other things are called orbits, periodic orbits, and they keep repeating themselves. So what about changing the multiplier to A, right? So if we change the multiplier A from 2 to 3, we're now getting a longer period of 16, but the number 5 is somehow missing, right? Okay. I mean, this is just to get you, and 5 becomes a fixed point, right? So this is just to tell you that just because you multiply and add, you may not even get a full period. And it's motivation for this basic result. So this is a theorem, and the proof is way beyond the scope of this course, but it's in this book. I highly recommend if you want to get yourself a Christmas present. It's the best present for, especially for PhD students. It's this book by Knut called The Art of Computer Programming. Volume 2 is on semi-numerical methods, and that's how I figured out a bunch of stuff. So I go there a lot. So there's a section 3.3 has a proof of this. So a lot of the examples are just nicked from there. So what this proof says is that it turns out that a linear congruential generator will have the full period if and only if, so it's equivalent a statement, if all these 3 conditions are satisfied, right? C and M are relatively prime or co-prime. That means the greatest common divisor of C and M is 1, right? This is very important. And the next property equally important is A minus 1 is divisible by all prime factors of M. I mean, prime numbers are like very, very important, right? They're like your periodic table for integers. I mean, they are the fundamental building block in mathematics in some sense, right? So you take M and you break it into factors and look at the prime factors, and then A minus 1 is divisible by all the prime factors of M, and then A minus 1 is a multiple of 4 if M is a multiple of 4. So these are the properties. And then different conditions apply when C is 0, but let's not worry about that detail. So SageMath has a function called GCD, right? So if I ask what's GCD, it's the greatest common divisor of A and B. So what is it? GCD of 7 and 17? 1. They're relatively prime too. And then what are the prime factors of M? So M is 17, so the only prime factor is itself. So then we have prime factors of some other big number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So you can do whatever. So this is a fundamental theorem, right? Number theory. So any number can be written as product of prime numbers, called the prime factors of the number. Okay, so then what we are going to do is, instead of assigning each at a time, we will just do this tuple assignment. So MACX0N gets 256, 137, 123, 13, and 256. Okay, so this is from Knut, I think. So we just assign all these numbers, and then we can ask what is the greatest common divisor of C and M. Okay, that is indeed 1, so that's good. They are co-prime. What are the prime factors of M? It's just 2. And we have to check that the prime factor A minus 1 mod 2 is divisible by 2. And that is because 136 is even. And then we do a list comprehension check for an M with more prime factors, right? So, if I have more prime factors, I can just do this. In this case, it had only 2, but this will work for checking using list comprehension. And then we do this other check, is M a multiple of 4? And if M is a multiple of 4, then A minus 1 is also a multiple of 4. Okay. I mean, this is not proof. This is just telling you one instance of the theorem being true, but okay. It's just recalling some basic syntax, okay? So therefore, these parameter values satisfy all conditions, and to have the maximum period length m. So, okay, so so here is just another one. So I'm going to call my lincomgen on this, and I'm going to print out the results of the list output by our linear congruential generator with these values that we are happy with. And we can turn that into a set if we want. And as we can see, it has all the 256 elements once we've ordered it turned into a set. Or you can just, okay, and it's, of course, the actual sequence is hopping around. Okay, so our LCG is an example of a good linear congruential generator. The next example demonstrates what can go wrong. So if I have this value for MAC x0n, and you know, but now a minus 1, which is 135, is not divisible by 2. So then we get into a fixed point at 91, no matter where we start. So this is just showing that, you know, just by a little code, that if the conditions are not satisfied, yeah, no problems. Okay, so this one is from Knut actually. Yeah, this one is 256, 137, 0, 123, and 256. So this is our LCG Knut 334 thingy. And we have that. And then when we turn this into a set, so yeah, so our LCG has maximum period length of 256, but this LCG Knut has period of 32. And let's look at them as points, okay? So we can plot them using our basic method. So I'm going to have a zip of the range 0 to 256 of our LCG list, and also this other one with a smaller period. And I'm building these tuples. Now I'm building these tuples so that I can pass them to these graphics methods, right? So I'm calling this points, and I'm doing our points to plot, which is this zip of pairs, and point size 1, and then I don't know. I'm starting to now write this new primitive called text. So if you ask, what is that? Insert cell above. So it returns a 2D text graphics object at the point xy. So you can just start writing things on the plot. Okay, so I just chose some place to put this text and put that text. And I'm choosing black color for Knut, and the default color is blue for the other guy. Okay, so you see I made all of these graphics objects, and then I'm showing this way, right? This is, again, a new function, but it's not too hard. So I use the show to actually render it. And then I'm using this function called graphics array. So if you want to put a bunch of plots, it's an array. Use this. So the graphics array has this tuple, which has the first element is p1 plus t1. So I'm just, superimposing these graphics primitives. So plot 1 with text 1 and plot 2 with text 2, and tell what figure size I want. Okay. So this is exactly where these 256 points are falling. Okay. And if you look at our LCG, it's kind of all over the place. But if you look at this bad example from Knut, it had a much smaller period. So you see it's repeating again and again. You see these repeating patterns. So that's why we want full periods. Okay. Okay, so So because we were we were using modular arithmetic in Sage, the numbers in our list are actually going to be these integer mod ints. So we have to, if you want to turn them into double precision numbers, we can do it using RR. Then that'll give us, multi-precision floating point real number representations of the mod number. So you may have to go back and forth between these types. Right, otherwise this division means something else. So we're now going to scale this because, of course, we want these numbers to be between 0 and 1. So we simply divide the one with the longest period by 256 by m, right? And then we're going to get numbers scaled between 0 and 1. Because remember, our goal was to produce uniform samples from the fundamental random variable. Okay, so that's what that is. And it looks a bit ugly. So, but because it's only 256, so there's lots and lots of zeros, so we don't need all that zeros. So you can do dot n digits equals 8 and just make it smaller if you want. Okay. So that's basically rolling your own pseudo-random number generator from scratch, right? I mean, we don't need to do this all the time, but you need to at least do it once. So this is our points to plot. Scaled, right? Now I'm doing the same thing. I'm zipping range 256 to our LCG scaled, and the same thing. I don't put any text or anything. Now you see, as I keep moving around, my numbers are falling all over the place between 0 and 1. That's exactly what is happening in the most sophisticated pseudo-random number generators. Of course, it's not just a multiplication and addition anymore, what you do, but it's the same thing. Okay, so then let's look at the histogram of this. So we're going to use PyLab, which is like kind of on MATLAB, I guess. So it's Python. It's a bit more than NumPy, because NumPy is slightly, for numerical computing alone, but PyLab comes with a bunch of plots, like matplotlib-like plots. So it's nice. It has like other functions like histogram and things that are not in NumPy directly. So let's import PyLab. And then we can clear current figure using this pylab.clf command. And then we can simply ask pylab.hist to give us a histogram of these numbers in our LCG scale. Right? These are just renormalized numbers in the unit interval. And then I'm going to give the number of bins here to be 40. Okay. So and I can put some X and Y labels and title, and if you do this save fig thing, which you don't know if you really want to, but if you want to save an image in your directory, then this is very useful. So it'll actually write a PNG image, I think. Yeah, in the directory. So if you look at the directory, there should be my hist, wherever you're running this from. It's very helpful. You see my hist.png. So anyway, or if you don't put that, you can just show it. So as you can see, this is kind of uniform looking, right? But there are these weird periodic effects. Okay. Because if it's a perfect sample from the uniform, then you will expect the histogram to be nice. Okay. And same thing, let's sort of do this for Knut's bad example. So that was a plot, and then if we look at the histogram for it, it really looks terrible. Right? There's just holes in places, and yeah, it's just the same thing is getting repeated again and again. So just seeing pattern. Okay, are there any questions up to now? Okay, so 256 is kind of bigger than 17, but that's not enough, so we have to go to much larger linear congruential generators first. Although we will not be using linear congruential generators for any of our simulations soon, this is very simple, so it's still used heavily, especially in the graphics community, because the arithmetic overhead is so low. It's implemented in the GNU Linux family, for example. So what you should maybe know about is this very infamous linear congruential generator called RANDU that's shipped with systems. I don't know if it's IBM or some major manufacturer have this RANDU. RANDU was infamous because it had the full period and all of this stuff, but then when you start looking at other properties of pseudo-random uniformly distributed numbers, it got really bad. Okay, and I'll tell you what these other properties are in a sec. First, let's encode RANDU. So RANDU has MAC X0N to be these numbers. So now you see this is huge, right? What is this? Oh my God, 2,147,483,648. It's a lot. And okay, it satisfies the conditions and all of that for the earlier theorem. So let's call that RANDU. So it has full period. And then let's just make a histogram of it. That looks pretty, pretty good because we only are looking at 10 samples. Okay. So the histogram looks okay. So let's just, let's first turn this into a PyLab array. PyLab array or a NumPy array is basically the same because NumPy is really what's under PyLab. And so that's our shape. And let's resize this into 5010 divided by 2, comma 2. Right? So I'm just going to turn this into a bunch of two-dimensional points, right? Because I have a list and I take 2 at a time. And because I want to now plot consecutive values as points in an ordered, what do you call it, in a square. Because, what are we saying? We're saying that these numbers are coming from a uniform, x1 to x1, what is it, 5010. All these samples are IID uniform, right? So that means they are independent of each other. So what does that mean? That means if I plot them in pairs, x1, x2, say x3, x4, if I just plot them in pairs along the first and second dimension, right? This is uniform 0, 1, right? If they are independent, then then the joint density should be a flat line, right? I mean, it should be uniform in 2D and 3D and so on, right? Now we're getting into equidistributivity, which is a very strong property of a pseudo-random number generator. So then I should be able to plot points here and see if it looks uniform in both dimensions if I break it in consecutive pairs. That's where we're going next. So yeah, so now I have my, I'm zipping my RANDU PyLab thingy or NumPy thingy by just so remember this was the list, the slicing, right? So this is take every every element of all the rows at the first column, and this is all the rows at the second column. So now I'm just taking those two, zipping it. So I'm going to create pairs, right? So everything, so reshaped, and I'm starting to plot that. Okay. Now there's no notion of the order, right? But it's just plotted all in 2D like that. So that's how that looks. Okay, that looks pretty good, right? Looks like it's kind of uniformly distributed in both dimensions and RANDU shipped. But if you do the same 3 times, why not? Right? because it's supposed to be IID all the way, right? So let's just do that 3 times. I'm doing nothing different. I just use points 3D, which renders this JMOL thing, something from molecular biology people that's underneath Sage. And you can get this 3-dimensional interactive thing. I can just sort of zoom a tiny bit. You know, I can sort of turn this around. Now start turning this around and see if you find anything interesting. There you see. So cool. Look at that. It's like corn rows in Iowa or something. I worked in dairy farms in Minnesota, central Minnesota. And my favorite job for the summer when I was a freshman was, you know, when they have these irrigators. This is a really fun problem. So, you know, there's a big farm and then you have these irrigators, right? These are huge circle radius irrigators. They pump water and then they go through the system and then they pour water everywhere and then they circle around, right? And then the grass grows and the cow eats it and eat the cow, all that stuff. So what will happen to the irrigator is, so this farmer was very innovative. So he was pumping water from his own little watersheds he created. So it was full of gunk. So although he had lots of filter systems, the tiny gunks will finally get stuck in the pockets, you know, where the water comes out of. So my job was, I had one motorcycle, like a dirt bike, tiny one. So I had to go in the farm and guess which spigot is most likely stuck by the pattern that this thing makes, because the irrigator is actually a whole bunch of, you know, independently moving wheel systems, right? So then I had to climb up the thing, park my bike far enough, and then clean the thing. That was a fun job. That was like $16 in 1992. A lot of money per hour. It's dangerous, but it was really fun. And this is exactly how the corn husks will look like. So this is a fundamental problem, right? What is this? This means that when I look at triples of what comes out of RAND-U, although it has full period, it's not good enough, right? It's not satisfying the basic condition that even the triplets, consecutive triplets, are independent and identically distributed from the unit cube, right? This is uniform, cross-uniform, cross-uniform. So anyway, I think that's kind of the moral of the story. So even the best things we have currently, which is the whole world is sort of revolving around this one. We will see that one soon. It's called the Mersenne twister. Even that has limits, right? I think, let's see. This is important to know. Okay, so equidistributivity. Showing results for equidistributivity. Interesting. Equidistributivity. Of E G. Okay. Yeah. Equidistributed. Okay. So this is the. So let's go here. Control F. Okay. So the Mersenne twister is a 623 dimensionally equidistributed uniform pseudo-random number generator. I'm not going to define what equidistributivity is. That's but this is the beginnings of understanding equidistributivity. So it should be, you know, equidistributed. And this is pretty much the state of the art. One of the state of the arts random number generator that everyone uses. It's already 1998, right? Matsumoto, Makoto, and Nishimura Fuji. And things are very complex in the field. So if you're doing like much more complex simulations, you need to make sure that these pseudo-random number generators up to provable equidistributivity limits that they pass actually are now coming from multiple streams. So you can't use just one stream. And these things matter a lot if you're, you know, deciding something fundamental like potatoes coming to grocery stores and you really need that much entropy. There is like a whole bunch of community people study this stuff. There's a whole ACM transactions devoted to this modeling and computer simulations and stuff. So that's way out of my expertise, but I just want you to, yeah, know that there's a lot can go wrong if you just use computer somehow. Okay, so here's So this one is actually a better one. So this is in the GNU compiler collection. This is also a linear congruential generator. I told you people in graphics use this a lot, and for graphics, you know, it's not as serious as potatoes, right? So it, so here M is 2 to the 32, and these are your A's and C's and so on, and it's a lot better, at least in 3 dimensions. You don't run into these kinds of problems, and then graphics is basically 4D, right? So objects moving in 3D basically is a movie. So okay, I don't know, you can't find anything crazy like RandU problem, but if you use RandU for graphics, that's kind of not going to make a lot of movies. Okay, yeah, so this is just visualizing the histograms here. Oh, what time is the fika break? Oh, we are going longer? Oh, right, sorry, I was just enjoying myself. I had beer, what do you call it? Rulon has beer today, finally. Yeah, let's stop and have a fika break.